are piecewise functions that are equal to and not equal to. So let's just start with evaluating to kind of get a feel for what the piecewise function is saying to us, and then we'll look at the graphing piece. So f of -4, we're looking at this part of the piecewise function to tell us what to plug it into. So either -4 is not equal to -3 or it is equal to -3. Well, clearly it's not equal to -3. So we use the first piece. So our answer here is -6. So on our graph, we would have the point -4, -6. F of -3, -3 is equal to -3. Now this is a little bit different. Sometimes you'll be faced with this with a piecewise function. There's no x. There's nothing to truly plug into. It's just when x equals -3, the value is 1. There's no plugging in, there's no question, that's just, it is what it is. So that gives us that point, -3, +1. 0 is of course not equal to -3, so we plug it into the first piece, and we get -2, so 0, -2 is a point. 5 is not equal to -3, so 5 minus 2 is equal to 3. So we have the point +5, +3. So hopefully with just plugging in those 4 points there, you're starting to get a picture in your mind that the only time I use the second piece is when my x value is -3. Any other time, I use the first piece. Now, I think the reason why it confuses people so much is because of that not equal to. You think with the not equal to that means that you're not supposed to use it or something like that. But it's just saying when your x value is not -3, so that means any other time except a -3, you use the first piece. So let's plot these points that we've got here, -4, -6. -4, -6, -3, +1, 0, -2, and 5, 3, 2. Okay, so let's go back to the equation for just a second. Our equation is x minus 2, so it's a linear graph. So that means that we can connect these dots right here. It has a slope of 1. So we can connect these points except at -3. So I'm going to kind of pick up my pencil here when I'm drawing this, and I kind of just left a little gap right here because the piecewise function says x cannot equal -3 when you're using the line of x minus 2. So now, by graphing it by hand, I know exactly where that's supposed to go, where that hole, where that open circle is supposed to go on my graph. I can see that it's supposed to go at -5, but I can also check that. If I plug -3 into that equation, -3 minus 2 is -5. That's where that is supposed to go, but my function says at -3, you don't use the line. At -3, you just use that value of +1. So that's what these graphs look like. Okay, the equal to and the not equal to's, they are going to look like the not equal to piece, except at one specific point. Okay, you might want to make a note of that. It looks like the not equal to piece, except at one point. So the vast majority of the time, these equal to and not equal to piecewise functions are not going to be continuous. Okay, and this one definitely is not continuous because if we were to trace our graph here, we would have to pick up our pencil when we get to -3, put that one little random point up there, and then jump back down to our graph to continue drawing our function. So this is definitely not continuous. Any questions about how I graphed that, how I found that hole, anything of that nature? Okay, let's look at another one. We've got -3 when x is not equal to 0, and +5 when x is equal to 0. Now, this is a very simple example, but it tends to throw people for a loop just because there aren't any x's. They don't see what they're expecting to see, so they think that they're missing something, but they're not. All right, so g of -4. -4 is not equal to 0, so we use the first piece. The first piece, there's nothing to plug into. It's always equal to -3. It is always equal to -3. So -4, -3 is our point. G of 0. 0 is, of course, equal to 0. So that is the second piece. So its value is 5. So 0, 5. 3 is not equal to 0. So we use the first piece. The first piece is always -3. So +3, -3. And for exaggeration's sake here, I did g of 100 just to prove a point. I know our graph doesn't go to 100, but just to kind of get that mentality in you that it's any number that's not 0, the answer is -3. So if we were to be able to graph that far, we could graph the point 100, -3. So let's see here, let's plot what we've got. -4, -3, 0, 5, 3, -3, and again, 100, -3 is off the charts there. So our function is always equal to -3, so we've got a horizontal line here, except it's 0. You gotta put a hole there, put an open circle for that missing piece, because we cannot equal 0 for this piece of the function. And when we do equal 0, our y value is 5. So that's that random point up there at 0, 5. So kind of a weird looking graph, but that's what it says. Functions equal to -3 as long as we're not equal to 0. When we are equal to 0, our functions equal to 5. So this one obviously is not continuous as well. As far as fixing the discontinuity, for the first one there, if we were to make that second piece, instead of the second piece being equal to 1, if it were equal to the -5, so I'm going to write that down here. If we change this, leave it as x minus 2 when x is not -3. But if we change that to -5 when x does equal -3, then that would fix our discontinuity here, because that is the value. -3 minus 2 is -5. That would plug the hole. That would fix the discontinuity if we change that second part there. Similar case, now the second one's a little bit more, a little boring, because it's just a constant. But if we change this, if we change the second piece to -3, then that would fix the discontinuity. Like I said, that one's a little boring, but that would fix the problem. Okay, any questions with the equal to and the not equal to? Let's look at the back. On the back, you will see we've got some three-parters. There are 3 pieces. I'm struggling with my braces this morning. Here we go. That's me. Okay, there are 3 pieces to the piecewise function. It does not change how we evaluate it. It really doesn't change how we graph it either. We're just going to have 3 different lines instead of having 2 different lines. So let's look at this one. F of -4. -4 would be less than -2, so that fits into our first piece. 2 times -4 plus 4. Negative 8 plus 4 is negative 4. So negative 4 is our point there. Negative 2 is equal to negative 2, so we stay with the first piece. That gives us 0. 0 is between negative 2 and positive 3, so that's our middle piece. And our middle piece is just equal to 0. So 0, 0 goes right there. And then 5 is greater than 3, so that goes with our last piece. Negative 4 times 5 plus 12. Negative 20 plus 12 is negative 8. So 5, negative 8 goes on our graph. So like we've been doing, let's start with our points that we got from our evaluating, and then we will add more detail where needed. Okay, so again, we're not just connecting these 4 dots. We've got different pieces defined for different values. So our first piece is when x is less than or equal to negative 2. So that's good. We have negative 2 there as we've already got that point. So I'm just going to, it's less than, so I can go to the left of that point, so I can connect those 2 points that are on the left. That covers my first piece. Our second piece is between negative 2 and positive 3. We are always equal to 0. And let's see here, at 3, it does have the equal to at 3, so I go all the way to positive 3, and it is equal to, so I put a solid point there, and it's always equal to 0, so it's just a horizontal line. And then our last piece is when x is greater than 3. So even though we're not equal to 3, though, I need to know where I start right there. So I'm going to plug in 3 anyways. Negative 4 times 3 is negative 12. Negative 12 plus 12 is 12. Or, excuse me, negative 12 plus 12 is 0. Sorry. So we pick up right where we left off. So I don't actually have to put an open circle there because I already have a point. I'm just going to use my slope of negative 4, so I'm going to go down 4 and over 1 to give me just a little extra point there to connect these two and finish out my function. Okay, so this one is continuous. All 3 pieces meet up to make one solid graph. So this one is a continuous piecewise function. Start on the left, I can trace the entire function without picking up my pencil. No breaks, no jumps, no issues. All right, let's look at the other 3 piecewise function. We've got 3 when x is less than 1. So negative 4 is obviously less than 1. So the value there is 3. So negative 4, 3 is a point. 1 is equal to 1, so that's the middle piece. 1 minus 5 is negative 4. 1, negative 4. 3 is between 1 and 4, so we plug that into the middle piece. 3 minus 5 is negative 2. 3, negative 2 is our point. And 4 is equal to 4, so that goes in our last piece. The square root of 4 is 2. So 4, 2. So start with these points again. Negative 4, positive 3, 1, negative 4, 3, negative 2, and 4, positive 2. Now, I purposefully chose these points just to get us a variety of using the different pieces. If you are having to graph one of these from scratch, do the same thing. Just pick some points in the different regions that'll give you some variety. and then figure out what other details you need from there. So for example, with the first piece goes until we get to +1. It's not equal to +1. So we've got the horizontal line at 3 until we get to x equals 1, and we want to put an open circle there because the y value would be 3 if we were equal to 1, but we don't actually equal 1. We just get as close as we can. That's as far as we can go. All right, so we did plug in 1, so we have the starting point for the next piece. We need to find the ending point for that piece. So the ending point of that piece is 4 for our x. So 4 minus 5 is -1. That is where we're going to have an open circle. And that doesn't very much look like a hole. There we go, that's better. Okay, so we start at our x of 1. That point down here at 1, -4, and we stop at 4, -1. So we just have a little piece right here. And then our last piece starts at 4, and it continues, and it is the square root function. So let's see here. The next perfect square would be 9. I'm going to go off the grid just a little bit to positive. The square root of 9 is 3. And I know the square root function is supposed to have some curve to it, so try not to connect those in a straight line. Do try and give them a little bit of a curve there. So this one obviously is not continuous. None of the pieces meet up. None of them are at the same y value at the changing point. Even if one of them did, both of them would have to meet up in order to say that that entire function is continuous. Okay, so even if, let's say, over here at +4, so those two pieces did meet, but at +1 they still didn't, it would still be not continuous. Okay, it's got to be continuous. It's got to meet at all changing points. Okay. I'm not going to worry about the fixing the discontinuity on this one because we'd have to do a lot of manipulating. What I do want to show you is I want to show you the power of Desmos. Okay, so I have shown you how to graph these completely by hand, and I do believe that that's a skill that you need in pre-calculus, but I do want to show you, in case you didn't learn or you have forgotten since Math 3, that Desmos does do piecewise functions. So let's do that second one there. It was equal to 3. Well, I got to do y equals. If it's a constant, you have to type in y equals. Otherwise, you don't have to have the y equals. You're going to put a brace. Okay, so it's shift, and it's somewhere around your enter button should be your brace. And you put in the inequality. X is less than 1. Okay, and then you close your brace, and look what it did. It graphed that line, but it stopped at x equals 1. Our second piece of this function, what was it? X minus 5 between 1 and 4. So notice I didn't have to type in y equals on that one because it wasn't a constant. I could have. If you want to be in the habit of putting the y equals, that's fine. 1 is less than or equal to. The shortcut to doing that is you do the less than and then you hit the equal symbol, and it'll make that less than or equal to. Or you can go to the keyboard at the bottom, and the symbol is there as well. Less than x, and that was less than 4. So there you see the little piece down there that we graphed. And then our last piece was the square root of x. You can type in SQRT, or again, it's on the keyboard at the bottom, the square root of x. And that was when our x was greater than or equal to 4, actually. Now, you'll notice that the one downside is that Desmos does not graph the points and the holes the way that we're looking at it right here. Okay, so this confirms what we just graphed. If I zoom in a little bit here, if I click and drag to the end, then it'll show me the hole. It will show me the hole there at 1, and it tells me that it's undefined. Okay, and obviously I just get as close as I can if I want to figure out what that actual value should be, but this one's pretty obvious that it should be a 3. If I click and drag right here, When I get to the end, it tells me 1, -4. That one had a point, remember? And then, but if I go to the other end had a hole. It had an open circle, so it tells me at 4 it's undefined, and I can see pretty clearly on my graph that it should be -1. Look at your y values, see what they're getting close to there. And then here, again, we had a point for that last part because it was equal to 4, 2, and then it obviously continues from there. Okay, so you use the braces. Pretty much you type in what shows up in your piecewise function. You type it in, you just put the inequality part in a brace, and it will graph the piecewise functions. So it's very, very powerful there.